Welcome to the Network Visualization Lecture, part of the Principles of Data Visualization lecture series. In this lecture, we're going to be discussing network diagrams that will form the content of everything we're going to be discussing in this lecture. And so first, we'll have an overview of the different components that make up a network diagram. So there's really two major components that make up a network diagram. So you'll see the yellow circles on the top left-hand part of the screen. You'll see a visualization. Sort of looks like Tinker Toys. Some of you guys may have played with those as kids. Maybe an atom diagram, something like that. So what is this thing? So if we look at these yellow circles that look kind of like plotted points, these are what are referred to as nodes. Now, there are different names that can be applied to these as we have listed here. So the appropriate name that we use in computer science is a node. We can also call these a vertex in mathematics. In physics, it might be a site. Or sociology, it might be an actor. And then we also have links. So the lines that connect the nodes, the black lines that are connecting the yellow circles, those are known as links. And link is the proper term in computer science. In mathematics, we can also call those edges. In physics, bonds. And sociology, tie or ties. Typically, we refer to these as node link diagrams. We take the computer science notation. It's most closely aligned with our discipline in business. And so we will use that notation. As we get into some of the tool sets, you will see some of the other synonyms, particularly edge, will be utilized sometimes interchangeably with links. But the principles are all the same and the concepts are the same, just a little bit different terms depending on the discipline. So the essence of our network diagrams is that node link diagram. Now, nodes tend to be objects. So they could be a person, some type of object. They tend to be nouns, some sort of object. And then the link describes the relationship between those two objects. So very simple example might be two of our yellow nodes there. It might be two classmates in our class, and the black line is the link that defines the relationship between those two people. Now, moving down to the center of the screen and toward the right, we have some descriptions, a couple of different types of network. So if we look just to the left, there's one that looks sort of like a backward C or an unfinished square. So that is a good example of what's known as a one mode projection. So basically there's just one class of object types visualized here. If we look over to the right, we'll see both yellow circles and red circles. And this is what's known as a bipartite network. So in a bipartite network diagram, we actually have two different classes of objects. So staying with our same theme, we might have our yellow circles up at the top. Those are objects. We've decided that we're going to use the metaphor that those are people, are members of our course. And then we might look at the red circles. Perhaps that's the car that they drive, or it could be the bike that they drive. the skateboard that they drive, perhaps something like that. But the main important thing is the distinction between we have two classes of objects there, people and transportation vehicles. And then we might have relationships between them. A good example on that very first yellow node to the right might be that particular individual has three different modes of transportation: a car, bicycle, and a skateboard that we have represented there. Okay, so just kind of recapping the different concepts of a network diagram. We have nodes that are objects, tend to be nouns. We have the relationships between them, known as links. We can have two different types of network diagrams. A one-mode projection is simply one class of objects, and then if we have a bipartite network, it's two or more classes of network. Now we're going to head into an example, network diagram. So this is a network diagram called They Rule. What this is a network diagram of the Fortune 500, the largest corporations in the U.S., and their boards of directors. So we'll see different boards of directors. So we see Google, Apple, Microsoft, and we see a boardroom table there. So that is those are our objects. Those would be nodes in our network diagram. And then we have individuals. So if we look off to the left, we have Tim Cook, the late Steve Jobs. We've got Andrea Jung. A little bit further up the screen, John Doerr, Eric Schmidt, Paul Otellini. So all of these are board members of these various boards. So if we take a look at those, we started with the Google board there. We can see that John Doerr, Eric Schmidt, and Paul Otellini are all members of the Google board there. And then there are also members of other boards. We can see Eric Schmidt's a member of the New America, a board member of the New America Foundation. John Doerr is also a board member at Amazon. And Paul Otellini is a member of the board at Intel. So this gives you a sense of how these nodes and links work together. So the board of Google, the board of directors of Google, that is a node. It is a particular object, as are the individuals of John Doerr, Eric Schmidt. Those are also objects. The lines in between Google's board and John Doerr and Eric Schmidt, those are the relationships of those individuals to the board. So what we're seeing there is different objects, and in here, this is a bipartite network because we have two different classes of objects. We've got board of directors as one class, and then we've got individual board members is another class of objects. This allows us, and now let's talk about, well, what does this allow us to do? So when we have a network diagram, one of the things that a network diagram is very, very good at is understanding an overview of a larger picture and all the relationships that are involved between different entities. And in this case, we can get a much fuller picture of what the existing boards are and who the directors are that serve on those different boards, and what are the other boards that they serve on. And a really good example of this might be the late Steve Jobs. We see toward the bottom left of the screen, who of course is founder as well as a former board member of Apple. As part of the Pixar acquisition, Walt Disney acquired Pixar, that Steve Jobs was also a board member of. Steve Jobs became a board member of the Walt Disney Company. And so you can see that individual has a relationship with the Walt Disney Company as well as a relationship with Apple. And so hopefully that that gives you sort of a real world sense of how would we use this network diagram. And that's just one simple example of what we can see in terms of the relationships of different board members on different corporate boards. And it gives us a lot more information and a lot better perspective on how the Fortune 500 are managed. Now we'll take a look at a little bit different example of a network diagram. Very, very good example, particularly of the utility of a network map and how useful it can be. So in this particular network diagram, this is a network diagram of different types of diseases. And the thing that's really cool about this network diagram is diseases that are all of a particular type are created as a class. And you see similar colored nodes to describe each of the diseases that are of a particular class. And then if you go to a different class of disease, it uses color encoding of a different color. It's also fairly thoughtful of when there are particular diseases that are part of one class but share some characteristics of another class, there might be some color blending that goes on, which is fairly interesting. And it helps us to understand the relationships between different diseases. Often we might take a particular disease and it has a relationship with a couple other diseases that may or may not be in the same class of disease. So that's fairly interesting. This is, as I mentioned, an overall map that was created by researchers that were linking different diseases, the genes that those diseases have in common, or how the relationships or the lines are formed between the different nodes. And down at the bottom, we can use the legend down there to help us understand the type of disease class that each of these is involved in, or related to, or labeling. As well, we have a scale. So the scale or size of the node, the different size of the circle, is described down in the bottom right. So each circle represents a disease or disorder and is scaled in proportion to the number of genes associated with that disease. So if there's a particular disease and it has a number of genes involved, it's going to be a larger node versus an alternate disease that may just have a few genes involved, would be a much smaller node. So let's go take a look at this from an interactive standpoint. So here we have the network visualization for mapping human diseases. So as we discussed, researchers created a map linking the different diseases represented by circles. Those are objects to the genes they have in common. We have color coding of those, as well as an application of scale that represents the number of genes associated with that disease. And so using our interactive tool here, we can look at some of the relationships between different diseases. So if we're looking at Alzheimer's here, we might have, looks like there's some relationship with heart attacks, hypertension. It looks like there's some sort of relationship with schizophrenia. Who knew? As well, we might have different types of cancers that might have relationships with some other types of syndromes or diseases. So we can see here with cataracts, a particular disease of the eye, it might have some relationship with myopathy. Some of these diseases in another class, but there's some genetic relationship between them. So it's a fairly interesting and neat way to look at different diseases. We can see the color coding down at the bottom, so different types of cancers. So these are classes of diseases. We have some bone diseases, skeletal, that are also color coded, skin, endocrine, gastrointestinal. So we might have particular relationships. You'll see these relationships between obesity and diabetes. So it provides us a unique look at the data that we otherwise wouldn't have been able to see. So this network diagrams provides a new perspective on looking in this type of data, where historically the data might have been reviewed simply within the class. So we know something's a particular cancer, maybe it has relationships with other cancers, but we may not have looked outside of it to see what are some of the relationships with diseases outside of its particular class, and what can we learn from those dynamics. Now, hopefully you guys have a better appreciation of how a network diagram works from an interactive standpoint. Now we're going to take a look at one of the best pieces of software, best software applications to create detailed network diagrams. So this application is called Gephi. It's an open source network visualization software application. It is written in Java and uses a 3D engine to display graphs in real time. And it reads a number of file formats. Of course, it's native Gephi file format, as well as Excel, CSV files, and some other unique file format types. And this is probably a good example. In some previous lectures, we discussed the importance and the utility of being able to reformat and repurpose data files for one application or another. And this might be a really good example where we have this very powerful tool in Gephi, but we might need to reformat a data file so that we can utilize it. Now let's focus in more on the network concept. So in a network diagram, every network consists of objects and the associations between them. Okay, so these particular objects on the right-hand side of the screen, we have one labeled A and one labeled B, are referred to as nodes. And as we've described before, these are unique identifiers of an object within a data set. So there's some type of object. We're describing something. It could be people, board of directors, boards, classmates, the transportation that they use, could be diseases. So you guys have seen a few examples how we might represent objects or nodes. Then we have associations. So our associations we discussed are links. Basically, that's the relationship between the objects. In Gephi, these are called edges. It's simply a synonym, just a different name for that relationship. So we could call it a link or an edge. And it's a line that connects the two nodes and establishes the relationship between the two nodes. And as we walk through our discussion on using Gephi, we'll be discussing these as edges, but know that they're the same thing as links or relationships. So as we discuss relationships, there can be different kinds of relationships in a network diagram, and we can differentiate between strong and or weak relationships in a network diagram. So here in our visual and conceptual example, we have different nodes, A, B, and C. Then between A and B, we demonstrate a strong relationship between the A and B nodes. So I want you to focus in on, we have a much thicker line that we're representing here. And here we're utilizing Bertin's principle of utilizing a line. It can be thinner or thicker. In this case, we're encoding more thickness in the line to demonstrate that there's a stronger relationship between A and B in comparison to the relationship between A and C. So if we look at the line or the arrow between objects A and C, we're defining a much weaker relationship there. And when we take a look at both of them side by side, we can see, okay, yeah, we are doing something there on the right. We're saying that must be much stronger. We have a lot more visual emphasis there than the one on the left that looks much thinner and sort of a weaker relationship. And so this is an important concept, and we're gonna talk a lot more about how we define or measure and assign the strength of relationships between our nodes. Now, as we begin to structure our network data, we're going to have two types of tables in Gephi. So the first one is called a node table. Alternatively, we could call it an object table. So in our node table, that's going to define all of the objects that we want in this network diagram. So basically, we're going to define each of those objects. We're going to give them a unique identifier as well as their name. So we must maintain that unique identifier for each. And then as a description, we're going to put a label for each of those unique IDs. So that's going to form our node table, and basically what we're describing here is all of our yellow circles, A and B. So if we were to create a node table for the diagram to the right, we just have two entries, maybe a unique ID of 1 and a label of A, and then a unique ID of 2 and a label of B. Now once we've finished with the node table, we'll then move on to the second table. And that table is called an edge table, and we could also call it a link table. And in the edge table, we're going to define the relationships between these objects in the network. So when we define an edge table, we essentially define it with the source and the target. So we're going to include the unique identifier of the source. So in this case, our source would be node A, and then our target, or the end node. And in our example, this would be node B. So we might have in our edge table basically a 1 to 2 source to target relationship that we've established there that basically is describing that particular edge or link that is between A and B. And this is what those two tables would look like. So in the Gephi file format, on the left-hand side here, we have our node table. Notice we have two columns, so our unique identifier, 1, 2, 3, 4. So basically a sequential number that we've assigned that is unique. And then the second column is the label. So we might have the different object names: homepage, world, register, technology, sports. And what we're describing in this one is different web pages. Then we move on to the table on the right-hand side, which is describing our relationships. So this is our edge table. And you'll notice that we have two columns, the source and the target. So the source is the object where the relationship begins, and then the target is the object where the relationship ends. So that's our from and to, just like it sounds, source to target. And in our example, that very first entry was source node 1 to target node 2. And we see that in the first row in this table. Now, a couple other things that I'd like to point out. So when we're describing those source and target unique identifiers, remember that these are coming from the node ID table. So the unique identifiers that we created in the node ID table is what we're using to populate the edge table. And so you'll see here in our example, on the left we have the unique identifier for the web page of sports, number 5. And you see that represented as a target for source node 1. And then you also see it as a source down at the bottom for target node 10 as well as target node 11. So this is the basic file construction layout for the two main files, nodes and edges, in Gephi. Now we're going to move on to a concept called node sizing. So as we've stepped through this, many of you have probably developed a curiosity about, well, why are some of the nodes larger than others, and what's going on with that? And so one of the unique features of a network diagram is we can size these nodes, these circles, larger or smaller to give particular emphasis to that object, sort of more or less emphasis. So in this example here, in our table, we have represented here nodes A, B, C, and then we've also represented the others, which would be D, E, F, G. Now, how have we sized these? So let's take a look at the other columns in our table. So for node A, it has 5 different links, or 5 different relationships, or 5 edges. So we can count those. So if we start with the node A, we see it has one relationship to node C, a second relationship to node D, and then 3 more relationships with node B. So altogether, it has 5 links, or at least the emphasis of 5 relationships. So based on that rating, it receives the highest or largest size of size 1. So basically A is the largest because it has 5 links. Now let's take a look at B. So the B node has 2 relationships, one to F and one to G. So basically 2 links. Now based on the fact that it has 3 fewer links than node A, we're going to give it a slightly smaller size. So it gets a size 2. Now let's take a look at node C. So with node C has 1 relationship. So basically a relationship between C and E. And so it gets a 3rd size that's smaller than B. So we assign size 3 to it, and it gets a little bit smaller node. And then for all the others, E, D, F, and G, they have no outward links. And so basically they have a 0 and are assigned size 4. Okay. So this is a simple example of how we could apply sizing to our nodes to give us some differentiation and understanding on which of those objects might be more important than the others. And in a network diagram, that's one of the things that we're trying to do. We're trying to differentiate between object A and object F, and we might say, well, which one of these has the most influence? And clearly, in this diagram, A has more influence than F. So you could also think about it in terms of popularity. So in our class, we might have students A, B, C, D, E, F, and G. Student A is certainly the most popular in the class, and so on throughout the different nodes. So here's an example of a network diagram in Gephi. So we'll see here at the center is our home page, and as I mentioned to you, we're visualizing a network diagram of a particular website and its relationships. So here we have the home page at the center. It has relationships with other pages. So technology, world, markets, register, sports, business, science. And so you get a sense of how these relationships are formed. We can also get a sense of the differences in the links, the relationships between the objects. We might, for example, look at the relationship between the home page and the technology page. So we see a very thick line there, which is telling us or communicating to the audience that there's a much stronger relationship between the home page and the technology page versus the home page and the business page, which has a much thinner relationship between them. So this is kind of how our network diagrams are going to work in Gephi, and hopefully gives you a feel for a good starting place using Gephi. Now the Gephi visual framework is really divided into 3 major sections, and we're going to walk through each of those. The first one is the Overview tab. And we're going to walk through that in detail, but the Overview tab basically, just like it sounds, gives us an overview of our network diagram and some of the different aspects that configure it. The Data Laboratory tab is where we're going to define what goes into the network diagram, and we're going to walk through examples of how we create those tables and how we structure the network diagram. And then the Preview tab is our, just like it sounds, more visual-oriented section of Gephi, where we're basically viewing and reviewing our network diagram without anything else complicating or cluttering up the screen. So let's start with the Overview tab. So when we click on the Overview tab, and you'll see the three buttons that we just discussed, the three different areas up in the top left-hand corner of the screen. So when we click on the Overview tab, we will be presented with a series of panes. We will walk through each of those. So we have some panes on the left-hand side, we have some on the right-hand side, and then the center section will be where we're building our network diagram. So let's walk through each of these panes. So on the top left, you'll see what is known as the partition pane. So on the partition pane, you'll see both nodes and edges. And these are going to be whatever we define as our data will be represented here. So when we define those two tables, the node table, if I click on the node tab, I'll be looking at these are all my nodes. And then if I click on the edges tab, I'll be looking at all the relationships that's coming directly from the data that we loaded. So that's known as the partition pane. So underneath that is the layout pane. So in the layout pane, we can choose a particular type of layout. And in network diagrams, we've got lots of different choices, essentially algorithms that we can choose to look at these relationships between the nodes in different ways. And we'll get into more detail a little bit later. But just know I can choose my type of network diagram here. In the top right-hand side, we will see basically different settings that we can adjust for our network diagram. So once we've set the type, we can also fine-tune our usage of that type of network diagram by changing some things. As an example, the average degree or average weighted degree, which basically you can think about it as an optimization or a dial to increase the importance of relationships between our nodes. Think about the statistic pane as a place where we can go to optimize and adjust and configure our network diagram. And then in the center, we have represented the graph area. And so this is where we're going to see our network diagram come to life as we begin to configure these different panes. Now, some additional things that we can utilize in our overview windows here. So the ranking pane. So you'll see right beside the partition pane is the ranking pane. So that allows us to rank our different nodes, basically which ones are the most important. Just like the example we had done previously where we ranked the A node is the most important. Then over on the right-hand side in the context pane, so that's going to give us some metrics on how many nodes are in your diagram, how many edges or relationships are there. And at the moment, that doesn't seem all that useful because we don't have a network diagram represented in the center of the screen. But it can become very useful as we begin to create a complex network diagram. We don't have to get out our pointer or use our finger to count how many nodes or objects may be in our network diagram. In many of these, there could be 1,000 or thousands of nodes. And what the context pane does is it keeps track of how many nodes we have and how many relationships or edges we have. Then the filter pane. So what the filter pane does, just like it sounds, it allows us to make refinements and adjustments to our network diagram. So there may be certain things that we want to filter out of our network diagram, certain relationships that don't matter as much to us, that we're not focused on, and at different times, just like we might use a filter in a dashboard or multi-dimensional data analysis. The filter pane here allows us to restrict what we're seeing based on our preferences. And a good example here might be restricting the visualization of nodes that have very weak relationships, as an example. So those most data sets, you're going to have strong relationships, weak relationships. For certain purposes, I may want to filter out all the weak relationships, or for other purposes, I may want to filter out all the strong relationships and focus on what are the weak links between the different objects here. Particularly when you get into social or social media type exercises, often the weak links are the most important ones. Now, an overview of the statistics pane. So we're focused, sort of focused in now on that statistics pane that would be over on the right-hand side to give us a little bit better understanding of some of the things that we can adjust here. So some of the parameters for network data, we can look at different kinds of exploration, different kinds of analysis, spatialization. So one of the most important aspects of a network diagram is how close or far apart we create nodes. So spatialization gives us an optimization of what we want to see there. Clustering, just like the statistical version, gives us a configurable element that allows us to adjust or optimize how nodes cluster together. And so if you remember back to our network diagram on diseases, we had clustered together different diseases that have similar genetic profiles. So that's an example of clustering, or how we might utilize that or apply it. How does the visualization in general, how is it displayed? And then how can we export our data? Now let's drill in on modularity class. So this is one of the elements that we can fine-tune. So the modularity class is a measure of the division of networks into groups. So I mentioned to you this concept of clustering nodes together. So if we have a higher modularity, it emphasizes dense connections between nodes within a cluster, and it de-emphasizes connections between nodes outside of clusters. So as we turn up our modularity, it tends to cluster related objects closer, and then it does not emphasize the relationships between clusters as much. So running the modularity class parameter creates this definition of clustering. So this particular parameter is what we use to define how we want to cluster these particular objects together. And here we have an example of that. We've made some adjustments to modularity here. You'll see over on the right-hand side of the screen the parameter of modularity. You see we've made a little adjustment there, and then we've clicked run, and it is adjusted the way clustering works in the center of the screen there in our graph, in our network diagram. Average degree is another parameter. that we can utilize. So average degree defines the number of unique relationships connected to a node. Now we can have different types of these average degrees. So we can have the average in degree. So that's the number of unique relationships that are flowing into a node. Okay. Now when you see out degree, it of course makes sense that we can also define average degree by the number of unique relationships flowing out of a node. So we could use that as a parameter. Or we could simply just take the average degree, which is the number of unique relationships regardless of whether they're flowing in or out. Basically, in and out relationships are all viewed the same way. So this average degree parameter is something we can run that also creates a definition for the clustering. Basically, looking at what is the strength of or collection or count of relationships that apply to a particular node. And let's take a quick look at an example of this. So we'll focus in here on node C. We have source and target. So here we're going to sort of capture this in three different ways so that we highlight each of these three different types of average degree. So the first one, average in degree, related to the C node, is going to be a measurement of 2, because we see there is a relationship flowing in from the A node and a relationship flowing in from the B node. So there are 2 in relationships, and that's how we express the average in degree for C. Now, the average out degree for C is going to be slightly different. So now we look at the relationships that are flowing from C to other nodes. And we will find that there are 3 of them. One from C to D, one from C to E, and one from C to F. So we have an average out degree of 3. Then we get to our general average degree. So our average degree doesn't distinguish between whether a relationship is in or out. It just counts all of the relationships. So in this case, there's 5. Our 2 in and our 3 out create the 5 relationships that C has. And that's the measure that we would express for average degree. Now, with each of these, whether it's average in, average out, or average degree, it's going to change the way the nodes and relationships are visualized. So here's an example of average degree. So the last one we discussed. So the node size is determined by average degree. So we don't necessarily distinguish between whether the relationship is in or out. Let's take a look at the first entry in our table on the left there, called homepage. So for the homepage, it has basically 8 degrees. So we could count those up. So starting on the home page, moving counterclockwise to the left. So we see there's a relationship to business, then marketing, etc., moving around counterclockwise. So 1, 2, 3, 4, 5, 6, 7, 8, ending on that last strong relationship with the technology. So basically 8 degrees. And so we assign a size of 1 to the homepage node. And you can see it is the largest in the picture. Next up, sports. So if we look at the sports node over on the right-hand side of the screen, the purple node, and we count the number of degrees that it has, we would count 1, 2, 3. And so with 3, we would express that's a size 2. So it gets the second largest node size on the screen. Then world and health. So we've got 2 others there. You can see those as the green nodes. So they each have 2 relationships. So if we look at health, it's got a relationship to the left there to money, as well as homepage. And then if we look at world, it's got a relationship to the homepage and to world news. So this gives us our third size. So the green nodes are just a little bit smaller than the purple sports node, but larger than the red nodes. And all the others, the red nodes, all have 1 relationship. And so we give it the size 4, which is the smallest we see on the screen. So hopefully this gives you guys a sense of how do we determine or assign sizing to our nodes. And we often do this with these measurements of average degree. Now, alternatively, we could take a look at using the in degree average. So we could instead choose average in degree, and look how much different our visualization is here. So when node size is determined by the average in degree relationship, so all of the others basically here we're emphasizing all of the other pages that receive information, in this case, from the home page. So the home page basically establishes a relationship, or at least 1 relationship in for each of these. And so we assign it a size 1. So all of the others, so technology, college football, soccer, sports, science, world, each of these receives an in relationship, at least 1 in relationship. And so they're assigned the larger size. The home page does not receive an in relationship from any of these. It actually functions as the hub distributing interest to these nodes. So it doesn't really have anything flowing into it. And so it's assigned basically a lesser degree of 0. It doesn't have any, and it gets a size 2. So it's represented as much smaller here. Now in our third example, this is probably a little bit more practical way that we're used to looking at the dynamics between web pages, known as average out degree, where the node size is determined by the average of out degree relationships. So here we have the home page, the number of out degrees that the home page has is 8. So it has 8 different relationships to other nodes that it provides information to. So we assign it a size of 1 because it's sort of the hub. It's the most important. Then for sports, it has 2 different nodes that it feeds. So it's feeding soccer and college football. And so we give it a size of 2. And then health and world, we assign, it feeds 1 other node, that being world news. So we give it a size of 3. And the same thing with health, that feeds money. We give that a size of 3. And then for all the others don't feed any other nodes, so we'll give it a size of 4. And so you've seen with these 3 different selections, whether it's the average degree, the in degree, or the out degree, it can significantly change the way our data visualization is represented. And what we're trying to do here is utilize the type or the configuration of each of these to help us solve whatever problem we're trying to solve, or to help us see whatever we wish to see. Now, with that understanding, we can also have what's known as the weighted average degree. And with weighted average degree, it's very similar to what we've just discussed with average degree, but it takes into account the number of unique relationships, including multiples. And so it's possible that objects can have multiple relationships. And so if you think about this in terms of web dynamics, how many different web page hits flowed from another web page? So that can give us a sense of, oh, so there were multiple hits, multiple relationships. There were 1,000 hits in a day versus 5 hits in a day. So that's what we mean by multiples. There can be multiple relationships there. And then we can also express this weighted average degree in the same terms, weighted average in degree, weighted average out degree, and weighted average degree. So the weighted average degree parameter runs creating definition for clustering, sort of the same way that we had discussed before. So to describe how our multiples works, we'll use this example again with node C. We'll be looking at the source and target nodes, but there's going to be one difference between this diagram and what we've done before. So notice that the link or the edge between nodes A and C now has a weighting to it. So that's a 2. And let's use a simple example of web page referrals. So web page A might refer users to web page C 2 times. Maybe it's 2 times in an hour or 2 times in a day. Then we look over at node B. B might refer to node C or web page C 5 times in an hour. And so we have relationship emphasis of B to C of 5 and a relationship emphasis of A to C of 2. And based on that combination, we have an average weighted in degree of 7. Basically, the 2 plus 5 provides our average weighted in degree. So remember that in degree is the number of relationships flowing into a node. So in this case, that's 7. Now let's take a look at average weighted out degree. So node C has a relationship with node D that has a weight of 6. So maybe web page C provides 6 referrals to web page D in an hour. Web page C might provide 3 referrals to web page E in an hour, and then web page C might make 1 referral to web page F per hour. And when we add all those up, 6 plus 3 plus 1, we have an average weighted out degree for node C of 10. Then finally, the average weighted degree that does not distinguish between whether the relationships are in or out is essentially just counting up all of the relationships that are weighted. So we have our 7 that are flowing into C, our 10 that are flowing out, so we add those 2 together, the 7 plus 10, and we have an average weighted degree, the general case of 17. Now let's take a look at the average weighted degree in use. So here our node size is determined by the average weighted degree relationship. So with homepage here, the number of weighted relationships that we have here for the homepage is 20. Now, the way that we get there is not the same way we did last time. So the same way we did last time, we just counted the number of relationships going clockwise. So our number of relationships here would be 1, 2, 3, 4, 5, 6, 7, 8. But here with average weighted degree, we include the number or weight of the relationships. And so we will notice that there's quite a bit stronger relationship between the home page and technology page, as there is a stronger relationship between home page and the science page. And when we're using average weighted degree, we include the weightings, the emphasis, how much stronger those relationships are. And so while we might have 1, 2, 3, 4, 5, 6 that have a lesser relationship, we have 2 of our relationships that are much, much stronger. And so we have a weighted degree of 20, which gives the home page a size of 1. Now, if we look at technology, we can see that its relationship is quite significant. It has a weighting of 10. So that relationship between technology and home page is 10. And so technology is provided with a size of 2. And if you're tracking back to the first example of both, how did we count up homepage of a weighting of 20? Well, we have 1, 2, 3, 4, 5, 6 sort of single relationships. We have the technology relationship of 10, which brings us to 16. And then if we look at the science relationship, it has a degree of 4, which gives us the total of 20. Now, proceeding on to sports. So sports has a relationship degree of 7. So we've got the individuals from homepage and college football that are singular, but then that relationship to soccer is quite strong with an emphasis of 5. So that gives us a total weighted degree of 7, giving it the third size. Then for soccer, as we just described, that's a weighted degree of 5, so we get size 4. With science, that's a weighting of 4, degree weighting of 4, and that gets size 5. Then world and health have 2 each, so it gets a size of 6, and all the others have 1 relationship to be provided size 7. So that's applying our average weighted degree. We can also apply an average weighted in degree. So now we're just looking at what's flowing in. So the node size is determined by the average weighted in degree relationship. And if you'll recall, we had this very strong relationship between the home page and technology, where the home page makes a lot of referrals to the technology page. So it has a degree size of 10 and is given a node size of 1. Then for soccer, soccer also has this strong relationship with sports. So sports feeds it 5 referrals, and it gets a size of 2. Science has 4 referrals from the homepage, so it gets a size of 3. The others, except the homepage, have 1 relationship flowing in, and the homepage doesn't have any relationships flowing in. So it is the smallest in terms of average weighted in degree. When we switch to the average weighted out degree, our picture, of course, changes. So the node size is determined by the average weighted out degree relationship. So this might give us an example of which one of our web pages is the best referring web page. And so, of course, our home page dispatches lots of referrals to other pages. It has a weighted degree of 20. So just in the technology, if you may recall, it has, an emphasis of 10. Basically makes 10 referrals maybe in an hour. So it gets a size of 1. The homepage gets a size of 20, and gets a size, its degree rating is 20, and so it gets a size of 1, the largest node size, because it has those 20 relationships outbound to other nodes. Sports has an outbound relationships of 6. So 5 to soccer, 1 to college football. So it gets a node size of 2. And then world and health have outbound of 1 relationship. So it gets a size of 3. And then all the others don't have outbound relationships, so they are assigned a size of 4. So hopefully with these 6 different examples of configurations that we can create, you get a better sense of how we can configure and adjust how a network diagram is displayed. One of the great things about network diagrams is it has a high degree of configurability, so that we can analyze exactly what we want to see. Moving on to the partition window. So in the partition window, as you recall, we will have defined our nodes as well as our edges, and then we can go in and assign different color codes to our nodes as well as the edges. And what we're doing here in the partition window is assigning color coding to nodes and edges based on parameters like their degree, modularity, several of the things that we just discussed. So in the ranking window, so we've just moved to the right of the partition. So our ranking can be calculated from different statistical parameters. We set the properties for the nodes and the edges. So on the top right-hand side of the screen, you'll see we're setting it for nodes. And then if you move down to the bottom right-hand side of the screen, we're setting it for edges. So the sizing criteria is defined from the drop-down. So you'll see up in the top right-hand window there that we've clicked on nodes. We're using the criteria of weighted degree for our assignment of color here. And then if we look down in the edges, so the bottom right hand window, we're assigning color here based on weight. So for our edges, whatever the weight of that particular relationship is. And remember, we can have different choices of average and weighted and that sort of thing. So the weight there, we're going to assign color to the edges. So basically 2 sections for definition, both nodes and edges, where we can assign the color codes for the nodes as well as the edges. Now with the nodes, we can open up a ranking window for the nodes and define a sizing criteria like out degree. Now we've been discussing these different criteria. Out degree, if you'll recall, is exclusively relationships flowing out of a node. So we can assign size to the nodes based on the out degree. So we'll see in the window in the bottom left-hand corner of the screen, we have here selected our nodes. You'll see that we've then chosen out degree as our criteria to define, and our ranking here. We'll assign color to the node label, and then we'll assign size. So now if we move up to the top right-hand window, you'll see that we moved from the sort of the font or color, and we're now focused on what is the particular size. We can adjust the minimum and maximum size, basically the range that we want to look at for our nodes. And then moving to the bottom right-hand side of the screen, we can define what size we want the label to be. So there's sort of three different pieces of how we can define ranking for a node. So remember, that's going to be a circle on the screen. We're going to give it a particular color. We're going to determine, okay, what sizes, and this is, you know, we can configure this. What sizes do we want on the screen? And here we've said, well, we don't want the size of those super small circles of 1 to 9. We just want to start with 10 up through 100, and that's all we want to visualize there. And then we can also define the label size. So it's possible for us to turn on labels for each one of the nodes, and we can define different sizes. It's, you know, the big label, the small label, that sort of thing here with this range. Now moving on to the filter window, as we discussed before, we may want to filter out particular values or attributes. So some of the filter criteria, we can filter on attributes, we can do dynamic filtering, filter on edges. For example, we might want to filter out less meaningful or more meaningful relationships. We can apply a filter to an operator or the topology or the way that the visualization looks. So as an example, we may want to filter by different attributes that are present in the node and edge table. So sort of a simple example, maybe I don't want my smaller or less significant relationships displayed, so I can just filter them out. And so here's an example of attribute filtering. So here we're filtering by degree. So if you recall, we went through this whole process of determining what the important or lesser important relationships were. We're going to filter by those degree measurements. So we'll expand the attribute folder. So over in the right-hand side of the screen there, we click on filter, click on attribute, and then we're going to define within the range folder. And then we're going to drag this degree integer down to the bottom to the query section. So once we drag it to the window pane underneath, it's now part of the query. And once it's there, we can click on the range and set the range that we want to view in our diagram. So here we've set the range from 2 to 8. Basically, we've filtered out our 1 relationships. If you'll see on the bottom left-hand side of the screen, this was our original network diagram before the filter. We applied the filter, and so you'll see in the center of the bottom of the screen our after image after we apply the filter, and notice that it's filtered out all of those single relationship nodes. So this is how filtering works. Now in the context window, as we described before, it will provide us with some statistics on what's going on in our network diagram. So number of nodes in the graph, here we have a simple example of 13 nodes, 12 relationships expressed as edges in between the nodes. So we have a pretty simple example here. For the context window, I also want you to consider examples where we might have 1,000 nodes or 500 nodes. And so having this panel that provides us some metrics on our network diagram can be very helpful when we're trying to communicate or express what it is, what the size and the shape of this network diagram is. Now, different types of graphs. So we also see there, okay, we've got some different settings of graph. So with a directed graph, it's a graph where the edges point in a particular direction. And so, as an example, if you recall, we might have in nodes, out nodes, or in and out nodes. We can have different types of relationships. So with directed, we're basically going to express whether it's an in or out. So by default, graphs that are imported from CSV files are considered directed graphs. But we can also change those settings and make it an undirected, and it's a graph where the edges are multi-direction. So all of the edges are considered multi-direction, where the direction of the relationship is not so important. Now, why might sort of direction be important here? So we have this type of network diagram that's become very popular called a force-directed network diagram. And what a force-directed network diagram does is it allows you to, for example, put your cursor on a node and basically apply force to that node and see how the rest of the network diagram responds to applying that force to the node with your cursor. And basically what's going on is it's simulating a physical system that spatializes a network diagram. So some of the most popular layout categories use force-directed network diagrams. It's aesthetically very pleasing. It has a high degree of interactivity, and so it's often utilized as an analysis technique. And the basic idea is to view nodes and edges clearly by moving the nodes further apart. So I might select a node, I drag it to one side of the screen, I get it off by itself, and then I kind of see how the relationships form as it regains its shape. So these graphs assign forces between the set of nodes and the set of edges. Forces keeps the graph in equilibrium. We're going to talk about those forces one by one. And to give you an idea, so imagine that each of the nodes is a steel ring, sort of a hoop, if you will. And then the edges represent springs that we've attached between the steel rings. So wherever that line was, we have a spring. The steel rings are forming the object. And imagine taking two steel rings and pulling them apart, and then letting go of one of the rings. The spring will make the two rings come back closer together. And so that's at the core of what is a force-directed network diagram. Now let's talk about some of the forces that make it work. So these forces in a network diagram visualization basically works on Newton's third law and applies it to visualization, where a force creates an equal and opposite reaction. So first let's talk about attraction. So forces act on oppositely charged objects, so pulling them together. So if we have a force of A on B and then a force of B on A, it's going to pull those two together. So you could think about two opposite poles of a magnet, maybe. Then repulsion. So forces act like charged objects, pushing them away from each other. So the force of A on B and then the force of B on A, look, those are both negative. So imagine trying to take two of the same poles of two different magnets, the negative poles, and trying to put them together. And what we experience when we do that is the two magnets shove away from each other. They won't, they have a repulsion. They just won't go together. There's a force that pushes them apart. So that's repulsion. And then the third force is gravity. So gravity is a force of movement toward the center. Now this gravity is the same, but when applied slightly different than the gravity we think of on Earth. So when we think of the gravity on Earth, it is a force that pulls us toward the center of the Earth. Basically, it sticks our feet on the ground. In a network diagram, in a visualization, what's going to happen with gravity is, let's say we pull those nodes apart, or we pull a node apart, it's slowly going to regain its original shape. And it's the force of gravity that's forcing it to regain its original shape. So what's this thing look like? We've talked a lot about it, and you're probably very curious. So we have two different frames of how force-directed works. So if we start on the left-hand side of the screen, that's our network diagram. We've drawn a highlighted circle around world, and imagine that we put our cursor on the world node, and then we drag it up to the left, the top left, and you'll see that image on the right-hand side of your screen. So notice that we've drug world up to top left of the diagram there, and what that is doing, this is an example of applying force to the graph. So when we're talking about this force directed, that's what we mean. We apply a force to it. So we will drag that node off, and then slowly the different forces that are at work that we just discussed will begin to reshape themselves back toward that world node. So homepage and some of the other nodes will begin to move sort of inch closer back to the world node, because that force of gravity is taking place again. Now the layout window. So in the layout window, we can choose from a number of different types or algorithms of network diagram layout. And you'll see in many of these are particular type of layout that a researcher has come up with a unique algorithm that helps to highlight different types or information in a network diagram. So these are display layouts. It is possible to create more layouts, and they can be added. So if you come up with your own algorithm, you can apply it here. And some of the selected examples that we're going to take a look at. The first one, the Force Atlas II. Second, Fruchterman Rheingold, and then the Yifan Hu. So the Force Atlas II, we've provided some guidelines for using it when you want to use this particular type. So it's an improved version of the Force Atlas with a single scale, and it allows users to set the repulsion levels. So remember, the repulsion levels is where we have the two similar poled magnets that push away from each other for spreading the graph, leading to better readability. So it's a good tool for network analysis or detecting behavioral patterns for very large networks. So what we did, and there are lots of different choices that we could have put in front of you, but we chose three examples that we thought you might utilize from a practical standpoint in your future projects. So if you have a very large network diagram, you need to select a type that visualizes it well. Force Atlas II might be a good choice. Some of the things that it suffers on, so it suffers on overall accuracy because it's handling this very large network of data. The graph is not is not always the same for the same network, as it changes with the state of the layout. So it's a little bit dynamic. The linlogs setting, so it's checked for linear attraction and logarithmic repulsion. And if you guys remember from our conversation on scales, you know what linear means and you know what logarithmic means. And we're just applying two different approaches or scales to whether it's attraction or repulsion. Now, unchecked makes clusters more tightly bound when unchecking the linlog settings. So that's a particular setting that we could choose. And then prevent overlap avoids larger nodes from obscuring view of the other components. So we've got a configuration choice here. And you may have experienced this before where you had particular circles or nodes, they're in the same location, and one of them is blocking seeing the other. Well, this prevent overlap is a configuration that we can choose to prevent any node from covering up another node. So here is a visualization of an Force Atlas 2. So its initial state is in our top left. That's the initial state, what it would look like. Then if we move down to the bottom left-hand side of the screen, if we want to prevent our overlap, we might check that setting and notice that the difference between the initial state and our new state is that in our new state we can see every single one of those nodes, where in the top left-hand initial state we see some are blocked or hidden from the other. And then finally, on the right-hand side, if we have logarithmic repulsion in linlog checked, notice how it basically pushes out some of those nodes. It still looks very similar to our representation on the bottom left-hand side of the screen. It's just got a lot more space in between our nodes there. So it's a little bit easier to read. Moving on to their Fruchterman-Reingold. So this is a standard algorithm. It's accurate, very easy on the viewers, so it might be more pleasing to a general audience. Some of the downsides of it has a lengthy runtime. So in order to understand and visualize this network data, the layout needs to be run for a period of time. But the upside of it, and the thing that makes it very nice, is its visualization is symmetrical. So it's a very symmetric view. It's much easier to understand. This is a very good algorithm for small or medium-sized networks, but not as suitable for large networks. And if you think about sort of the lengthy run times it needs to run for a period of time, the larger data set that you apply to it, the longer the runtime is going to be. Now, the Fruchterman-Reingold works on the principle of gravity. So you'll see that gravity principle and equal spacing applying itself as you use this particular algorithm. And it uses a single option called area function. So it either spreads the network apart or brings it closer together. And that places more burden on the algorithm, which is basically what its limitation is. So that algorithm is continually running to space out the nodes. So we want to apply this as appropriate. And this is what the Fruchterman-Reingold visualization looks like of a network diagram. So one of the things you may notice is that it has some very nice use of the space. It spaces all the nodes out. They're easy to see, easy to read. It's very symmetrical. And particularly for a small and medium size network or data set, it makes a very nice network diagram that's easy to read. And finally, let's take a look at the Yifan-Hu. So, one of the benefits of the Yifan-Hu is rapid computation speed compared to other force-directed algorithms. So it's easy to understand the approach for rapidly viewing small or medium-sized networks. It applies attractive and repulsive forces at the neighborhood level and uses a generic way to set the springs and nodes apart by setting optimal distance levels. It measures the relationship between attraction and repulsion using relative strength. So it's going to be basically netting those two. And here's what the Yifan-Hu visualization looks like. So a little bit different. We get some of those spatialization, so it does spread those out some. It's not entirely symmetric, but we do get some of the spatialization and probably pick up a little bit on speed with this type of algorithm. Now, moving on to, the data laboratory. So we've had a great discussion on the overview, how network diagrams are displayed, how we can optimize them. So now we're going to move into get a little bit more serious about building one. So as we click on our data laboratory is where we're going to load our data sets in. So we click on the data laboratory, then we're going to click on the nodes tab. So the nodes tab is going to display the nodes table. So we see that tab. If we look at the screen at the bottom, we have the nodes tab selected there. So that's going to display the nodes table. The edges tab is right beside it, so we can look at the edges table once we've loaded it. And then if we click on the Add Node and Edges button, it will add additional entries. So we can click on and add single entries if we'd like to add our data that way. We can search and replace any specific entry for the tables. So there's a utility there that allows us to do some maintenance. And then we can export the edges and nodes table as well. So if we want to export whatever data sets we have that we've created, we can use the export button there. We can clear graph and edges table. So if we decide, hey, we don't have the right data loaded, or we want to load a new set of nodes and edges, we can clear it. And then probably most importantly for everyone is the upload CSV or spreadsheet files. So if we look at the import spreadsheet tab, this is what we're going to utilize to upload your data sets. So by clicking on that import spreadsheet, it will bring us a particular window. We'll click on the ellipsis icon, so the three little dots that we have that button highlighted on the right-hand side of the screen. We're going to select the nodes file for import. So we see the second area that we've highlighted there is the nodes table. We've defined what the separator is going to be. So in a CSV file, it's a comma separated value. So we're going to select the separator as comma. We want to load this particular data file into the nodes table, and then we can define the character set that we would expect in the data file. So we will select the nodes table from the drop down as table. Click Next. and then adjust the data types as appropriate. When we click Finish, we can then go to the Nodes tab to take a look at the table entries. So once the node table is uploaded, we'll click on the Import Spreadsheet button again to import the Edges table. And here's an example of the Nodes table after the upload. If we clicked on the Edges table, we would also see the import of that data as well. So both of them work exactly the same. When we click on that import data, whichever we have specified, whether it's nodes or edges, will be loaded up into that table, and then we can view it with whichever tab we prefer. We can then look at the preview window. So when we select the preview window, so that's our third area in Gephi. So when we select the preview, it allows us to change the node label, edge, and edge label settings for the graph. So as soon as we click on preview, we're going to see our network diagram displayed in the center of our tool set there. And then to the left, we have a number of preset items, and as we've discussed, we can make adjustments to the way our visualization looks. Now, it's important to understand that Gephi works with browser visualization. So you can download the JavaScript viewer. We've provided the link here. You'll extract the folder, place it on the desktop or any other file location that is appropriate for your particular computer. You'll export the Gephi file. So after you've built your network diagram, you export that Gephi file. The file type is GEXF. Place the file in the downloaded JavaScript folder. And then you'll double click on that JavaScript folder and then open the config JavaScript file using a text editor. So you can use Notepad, Sublime, Eclipse, any of a number of different text editors. Probably my favorite is Sublime, but there's all of them will work sufficiently. You'll maintain your exported .gexf file as highlighted there to the right. So basically you just define, hey, this is my file name. You'll right click on index.html in the JavaScript folder and then select open with any web browser. And when you do, you will see your visualization, your network diagram displayed in a browser. There's a couple of navigation features, so we can zoom in, zoom out on our network diagram. We can activate and deactivate a lens. So a lens is sort of like a magnifying glass. And then if we prefer, we can toggle hiding and unhiding the edges or our relationships if it helps us perform a better analysis on our network diagram. So this has brought us through what are network diagrams, how do we create those network diagrams with the three major working areas in Gephi. So to summarize, Gephi is a network visualization and analysis tool. Our nodes are our objects, and we can have different classes of nodes. Edges are the relationships between objects. The size of our nodes depends on the number of relationships. So there's lots of different ways that we can configure how the relationships define the size of the node. The strength of the relationship between the nodes is depicted by the thickness of the edge or the line. So if you have thick lines, it's a lot more relationship than if you have thin lines. And then Gephi is divided into the three major sections. We have the Overview tab, the Data Laboratory, where we load our data, and then the Preview tab, where we can preview how our completed visualization will look.